Welcome to this presentation. In this model, let us have an insight of Inferior array. That is the array of n elements with the equal spacing and currents equal in magnitude but with progressive phase shift. Let us now find the phase angle between adjacent sources that is required to make the field at maximum in the direction of the array phi is equal to 0. An array of this type may be called as an Inferior array. For this, we can substitute the conditions psi is equal to 0 and phi is equal to 0. So, therefore, delta will be equal to minus dr. Hence, for an Inferior array, the phase between sources is retarded progressively by the same amount as the spacing between the sources in the radians. Thus, if the spacing is lambda by 4, source 2 should lag source 1 by 90 degree and source 3 should lag source 2 by 90 degree. So, as an example, the field pattern of an Inferior array of 4 isotropic point sources can be calculated by considering the space between sources as lambda by 2, that is delta is equal to minus pi. The field pattern in rectangular coordinates and the phase patterns will be similar to the Inferior array, and the same shape of field pattern can be obtained if delta is equal to plus pi. Since with the d is equal to lambda by 2, the pattern is bidirectional. However, if the spacing is less than lambda by 2, the maximum radiation is in the direction phi is equal to 0 when delta is equal to minus dr, and in the direction phi is equal to 180 degree when delta is equal to plus dr. And now consider a number of identical radiators applied with equal current which are not in phase, and assume that there is a progressive phase log of beta d radians in each radiator are shown in this figure. And consider the current supplied to first element A0 to be I0. Then the current supplied to A1 is given by I1 is equal to I0 into e power minus j beta d. Similarly, the current supplied to A2 is given by I2 is equal to e power minus j beta d, that is equal to I0 into e power minus j beta d into e power minus j beta d, that will be given by I0 into e power minus j into 2 beta d. Okay, and thus the current supplied to last element can be written as, in general, In minus 1 is equal to In into e power minus j into n minus 1 into beta d. The electric field produced at point P due to A0 is given by E0 is equal to IDL sin theta divided by 4 pi omega epsilon naught into j beta squared by R0 into e power minus beta R0. J beta R0. Okay. And the electric field produced at point P due to A1 is written as E1 is equal to IDL sin theta divided by 4 pi omega epsilon naught into j beta squared R1 into e power minus j beta R1 into e power minus j beta d. But R1 is equal to R0 minus d cos psi. If we substitute the value of R1 as R0 minus d cos psi, the E1 becomes IDL sin theta divided by 4 pi omega epsilon naught into j beta squared by R0 into e power minus j beta into R0 minus d cos psi into e power minus j beta d. So, if we separate this term, that is e power a into b can be written, a plus b can be written as e power a into e power b. So, E1 is equal to IDL sin theta divided by 4 pi omega epsilon naught into j beta squared by R0 into e power minus j beta R0 into e power j beta d cos phi into e power minus j beta d. So, the entire term which is given in this bracket can be written as E0. So as this value is given as E0. So, E1 now becomes E1 is equal to E0 into e power j beta d into cos phi minus 1. So, the condition will be referred to as the increased directivity. Thus, for the phase difference of the fields at large distance can be written as psi is equal to dr into cos psi minus 1 minus pi by n. The field pattern of an Inferior array of 4 isotropic point sources can be found as below, and the spacing between the sources is lambda by 2, and therefore delta is equal to minus 5 pi by 4, and hence the conditions are same as for the array with the patterns except that the phase difference between the source is increased. If we compare the field patterns, it is apparent that the additional phase difference yields a considerably sharper main lobe in the direction phi is equal to 0. However, the back lobes in this case are excessively large because large value of spacing results in too great a range in psi. To realize the directivity increase afforded by the additional phase difference requires that psi should be restricted in its range to a value of pi by n at phi is equal to 0 and a value in the vicinity of phi at phi is equal to 180. And this can be fulfilled if the spacing is reduced. For example, the field pattern of an Inferior array of 10 isotropic point sources of equal amplitude and spaced lambda by 4 apart for the phase condition giving increased directivity can be delta is equal to minus 0.6 into pi. In contrast to this pattern, we can present that identical antenna with phasing of ordinary Inferior array. Both patterns are allotted and to the same maximum. The increased directivity is apparent from the greater sharpness of the pattern. Integrating the pattern including the minor lobes, the directivity is found to be about 19 and the ordinary Inferior about 11. The beam width and directivity, we can compare it as the beam width between half power points for an ordinary Inferior array will be 69 degree, and for an Inferior array with the increased directivity can be written as 38 degree. Similarly, the beam width between first nulls for an ordinary Inferior array is 106 degree, whereas the beam width between first nulls for the Inferior array with the increased directivity is 74 degree. And the directivity of ordinary Inferior array is 11, whereas the directivity of the Inferior array with increased directivity is 19. So the maximum field pattern occurs at phi is equal to 0 and psi is equal to minus pi by n. So in general, any increased directivity Inferior array with maximum at psi is equal to minus pi by n has a normalized field pattern which is given by E is equal to sin pi by 2n into sin n psi by 2 by sin psi by 2. Now, let psi is equal to beta d into cos phi minus 1. So, if we substitute the value of beta d into cos phi minus 1 as psi, so that equation becomes E1 is equal to E0 into e power j psi. The electric field produced at point P due to A2 is given by E2 is equal to E0 into e power j into 2 psi. Similarly, electric field produced at point P due to an minus 1 is given by En minus 1 is equal to E0 into e power j into n minus 1 into psi. So, the resultant field at point P is given by Et is equal to E0 plus E1 plus E2 plus and so on up to En minus 1. If we substitute the values of E0, E1, E2 and E3 and so on, the equation becomes it is equal to E0 into E0 plus E0 into e power j psi plus E0 into e power 2j psi and so on up to E0 into e power j into n minus 1 into psi. So, if we take E0 outside as it is common in all the terms, so Et is equal to E0 into 1 plus e power j psi plus e power j2 psi plus and so on up to e power j n minus 1 into psi. Therefore, Et is equal to E0 into 1 minus e power j n psi divided by 1 minus e power j psi. If we take E0 to the outside and apply trigonometry as we did in this previous presentation, the equation becomes sin n psi by 2 by sin psi by 2 into e power j n minus 1 by 2 into psi. So, considering only magnitude, we get magnitude of Et by E0 is equal to sin n psi by 2 divided by sin psi by 2. So, the Inferior arrays can be found by substituting these values, and similarly in the first case, whereas in the broadside array that is a linear array with n isotropic sources of the same amplitude and phase, we get psi is equal to only dr cos phi, right? So to make psi 0 and requires that we phi is equal to 2k plus 1 into pi by 2, where k value ranges from 0 to 1 to up to infinity. So the field is therefore a maximum when phi is equal to pi by 2 and 3 pi by 2. This is the case in the broadside array, whereas in the Fanfare array the case is entirely different, which we have seen. So by considering the both the broadside array and endside array, the decision can be taken from by which where we need the radiation pattern to be maximized. Thank you. And similarly, now let us see some properties of Fanfare also. That is, a major lobe occurs at the direction psi is equal to 0. That is, by substituting the value of beta d into cos I minus 1 as 0. That is for the Fanfare array, where currents applied to the antennas are equal in magnitude, but phase changes progressively through array. The phase angle is given by beta d cos phi minus 1. In case of the Fanfare array, the condition of the principal maxima is given as sin is equal to 0. So, beta d into cos phi minus 1 is equal to 0. Therefore, when you take beta d to the other side, right hand side, cos I is equal to 1 and psi is equal to 0. Psi is equal to 0 indicates the direction of the principal of maxima, right? And the magnitude of the major lobe can be written as limit psi is equal to, psi tends to 0, d by d psi of sin n psi by 2 divided by d by d psi of sin psi by 2. And this can be written as limit psi tends to 0, cos n psi by 2 into n psi by 2 divided by cos I by 2 into psi by 2. So the major lobe is equal to n, where n is the number of elements in the array. So this diagram shows the radiation pattern of the Fanfare array. That is, the maximum radiation occurs at angle 0 and 180, and the minimum radiation occurs at 90 and 270. Thank you.